Well, theoretically, we're moving on through the book. I've got some kind of fun things today like a workout, a little bit of a workout to practice with definitions and convergence and stuff. And if you haven't yet, what you really should do is read it. We're going to start going through it today, but please read section 9.1, and I definitely have that done probably by the end of the week would be great. This is where we start really getting into using the definition of convergence, and things get very abstract. If you've got a lot of gusto, you could read through section 10, or at least start on it, because that's going to really push your brain. But I'm going to push your brain today, so take a minute, grab a piece of paper, and let's just practice stuff. It's unofficial, karma-free quiz. We say limit as n goes to infinity. So we have a sequence x sub n, a sequence of real numbers. We say that this is true if what? See what you can get. What's that definition? Practice writing that out. And then we're going to mess around with it. When you watch this, we're not meeting on Wednesday. Short story. I don't want to tell it on a recorded medium. But Calc 3 will meet. Calc 3 will meet on Wednesday. All right, we either kind of got that, or we have to recreate history of analysis at our desks in several minutes. Christian, you seem like you might have it there.
I said so x converges to L if for any epsilon greater than 0, there exists big N such that little n is greater than big N, implies that the absolute value of x sub n minus L is less than epsilon.
That's so good. Beautiful. Well done. How are we feeling about that? We got that definition down? Awesome. So that's where we say sequence x sub n converges to L if this happens. So this exercise I'm about to present to us is a twist on this, and it's from a different book, not our textbook. But I'm gonna give you a new definition. And so it's this is not standard. This is like a play definition, just for us to think about. So I'm going to say a sequence x sub n verconges, so just flipping the word a bit there, verconges to L if, and what we're going to do is we're going to flip the quantifiers. If there exists an epsilon greater than 0 such that for all capital N, that's a natural number, little n bigger than capital N implies x sub n minus L is less than epsilon. Write that down. Take a minute to process that. So I want to ask you some specific questions about it. I have to find where, yeah. And the first thing I'd like you to do is come up with an example of a Vercongent sequence. So you're really gonna have to think about what this definition means. I would think about those epsilon tubes and stuff like that. The picture's gonna help process this. So give one example of a Vercongent sequence. Picture. If I draw any more, kind of give away too much, I think. How you feeling about this? That's it. That's it. Good work. Yeah, what are you thinking? Well, see, so we've got, so there's this epsilon that exists that essentially, no matter what n is, the distance is going to be less than that epsilon. So there won't be any outside of it. Do you see? Yeah. So what's in it? Think about there's an idea that we've talked about that this is the equivalent to. How's it going, Steve? Oh, it's okay. So tell me how you're kind of like thinking about it, or what's snagging you. So let's think about what we got here. So we're saying, so looking at that picture up there, there's my L that's from the definition. And I've got these little dots, spread around that, moving to the right. And we're saying we can find some positive number, epsilon, so that no matter what n is,
Because notice how that says for all big N with little n bigger than that, that essentially says that no matter what n is, so if n is 1, this is true. If n is 2, for any n, x sub n minus L is less than that epsilon. So remember that this means I'm within x sub n is within epsilon units of L. So what does that picture look like? That's the thing. Think about the picture. How's it going, Lily? Okay, so is this your picture for it? Oh, okay, cool. Is this a different picture?
Yeah.
Okay, cool. That's good. That's good. So what you're thinking about this?
I'm not sure, honestly.
Okay, cool. So it's looking at that picture up there, right? So we've got this number L, and we're saying that I can find some epsilon so that no matter what n is, the distance between the dots and that L are within epsilon units. So I can find this epsilon. It's the flip of no matter what the epsilon is. So normally we say, no matter how tiny the epsilon is, I can eventually find some place where everything's inside there.
Right.
This is saying something different. This is saying that I can find this one single epsilon so that x sub n minus L in absolute value is less than that distance. Spend a few minutes thinking about that.
See, I'm trying to twist up something here for yeah, you kind of already got that, Christian. Well, let's talk this through. Because I kind of want to move on. I got a couple other play games I want to set up here. So we're saying we can find this one epsilon so that for all n, so for example, when n equals 1, if n, little n is bigger than that, I guess maybe the first one could not satisfy this. You could have x sub 1 outside possibly because of the way we do this. But I can find some epsilon. So plus epsilon minus epsilon. So that is essentially no matter what n I have, x sub n is inside here. And all the x sub n's are between L plus epsilon and L minus epsilon. So it's saying I can find an epsilon strip where everything lives inside. And what's the other word for that? What's another word for that? Christian, you had it.
So that'd be a bounded sequence.
It's saying essentially, yes, so this essentially means the sequence is bounded. And it's kind of a funny way to write it. So any bounded sequence, so it doesn't even have to be convergent. And I think you wrote down one that wasn't convergent, maybe. But let's take a look here. Let's say I had x sub n is minus 1 to the n. Give me a number. What number would this be? What if I said L equals 0? What is the epsilon that works? Give me one epsilon that works. So look at the sequence. And here's L. 2. So here I could use epsilon as 2. So if I go up plus 2 and minus 2, that would work. Is that epsilon unique? What's the smallest epsilon could be? What's the smallest epsilon I can have so that plus epsilon and minus epsilon live inside there? Is there a smallest? what would you kind of want to say?
Be like as close as you could get to 1.
Yeah, you kind of want to say 1, but we don't want to say 1 because we have strict inequality here. So if I have x sub n, let's replace our zeros. I don't want to put 1 here. Because that sequence doesn't work. But the key thing is, there just exists 1. It's not saying for all. So as long as this epsilon is bigger than 1, everything's going to be good to go. So 1.001, still cool. What if L, so let's go back to this sequence here. So still the same sequence. What if I say L equals 2? So still there's the 1, there's the minus 1, but now I'm saying L equals 2. What should epsilon be? How big, how wide a strip, what's the radius of a strip around 2 to make sure the whole sequence falls in there? What do you think, Camila? Yeah, so like how far down do I need to go to ensure that the sequence is in there? And then, of course, up the same way. So what is that epsilon I need to use? And there's lots of answers. But pick an epsilon so that if L equals 2, so in other words, I say this sequence x sub n for conjugates, sorry, I know this is confusing, to 2, what epsilon would work? There you go. Anything bigger than this distance here. So yeah, so 4 would work. So we could get epsilon equal 4. Notice you could use any L. So a sequence can conj to any number because you can always just find a response epsilon to just pick it big enough for that to happen. So that's a weird definition. Let's try another problem. So new definition. This one's gonna take a little bit of time. I'm gonna give you a little bit of time. Okay, so I'm gonna give you 2 definitions. And these are actually fairly reasonable definitions. They're not goofy. 2 definitions. The first one is we say a sequence x sub n is eventually, and these are be great words to use from time to time, eventually in a set A, which is a subset of R. This is getting a little abstract. If there exists an n, that's a natural number, such that A sub n is in A for all little n bigger than or equal to capital N. I'll just write it like that. It's good. It's good to play with. A little different than our normal definition. And then the next one is a sequence x sub n is frequently in a set A, subset of the reals, if there exists, if for all big N in the natural, so for every single one of these big N, there exists a little n bigger than or equal to that capital N, such that x sub n is in the set A. So today, a lot of practice about just taking a definition that's kind of weird and starting to wrap our heads around it. So, I've got some specific questions here for you. This will help a little bit. when you get weird definitions, you want to start just coming up with examples and counterexamples of those things. So to help you wrap your head around it, I'm going to get you started for sure. And I'm going to ask you some specific questions. One, is the sequence -1 to the n eventually or frequently in the set, and this set only has the number 1 in it. So on the real line, this is my set A, and A is just the number 1. So let's take some time and try to process this. Really stretch our brains a bit. I'll give you the second one, just in case. Little elusive question there. Let me get done with that first one. So here, the second question I'm asking, which of these definitions is stronger? In other words, which one has more constraint to it and implies the other definition? So if I have a sequence that's eventually, is that sequence also frequently in A? So if I say a sequence, x of n, is eventually in a set A, according to this, does that imply that this definition holds for it is true, or is it the other way around? Is a frequently eventually in A? It's good for our brains, definitely. And I'm happy to consult. If you have any questions, you need any clarification, you want to ask anything, let me know. Let's talk. You might want to draw a picture on the real line. Huh? Dots. Moving around, a sequence on that real line. See if you can discern the difference between eventually and frequently. Those words actually are very loaded. They imply pretty much exactly what the idea is. I'm sorry, oh, gotcha. So tell me what you're thinking is.
Okay, so we have the set point and negative one to the end will eventually be one. Like we
It
will
will,
find in the
definitely.
middle end
So,
that is eventually.
absolutely,
And so
yes,
that's kind of working with the definition
Okay.
of frequently,
yeah.
where it's like, is it gonna be there every time and yeah.
So let's check out that eventually, so I can find some place,
Mm-hmm.
some place for where, from that point on, A sub n is in the set A.
Mm-hmm.
Is that true here? Will, at some point, this always be one? So it's not eventually.
Mm-hmm.
See how that one's working? That one's saying that eventually, I live there.
Yeah.
Then what's this about? Now think about the other one. Yeah, yeah.
Okay.
You see?
Mhm.
Yeah.
What you thinking, Cliff?
I think, well, my thinking is
Yeah, why are you thinking that?
well, it does hit one,
Mm-hmm.
but isn't like always on. Like
Yeah.
there's no one, there's no point where it's like, it stays there, I guess.
Perfect. Yeah.
So then for the second question,
Yes.
would it mean like eventually implies frequently, but frequently does not imply eventually?
Nancy's.
The second question.
Got it? What are you thinking?
I was thinking frequently because since it oscillates, it never remains in the set point.
Perfect. Yeah, exactly. Are you still thinking about the second one now? Or do you got
Yeah, I'm
sense?
still thinking.
Still thinking? Okay.
Mr. Christian. Yeah, yeah. Yes, exactly. That's it. That's it. Good stuff. It's good exercise. That's fun. Let's see. There might be. Let me see if there's one more little third part to it. We'll wrap it up together. Okay, so one last question here. Everybody seems to be, this is going pretty well. This sequence, -1 to the end, goes, well, let's draw the picture out. Here's -1. It's alternating back and forth between those 2 points. So there's no cutoff point, there's no place in the sequence where from there on out it's always equal to 1. And I think everybody seemed to get that it's not eventually 1. However, it is frequently 1 because you tell me wherever you want to go into the sequence. So let's take a look here. It helps to have both imagings of this thing. And here's our set A, right here. The set A is just that point 1. So you tell me how far out to go. So I say, okay, for all n's. Okay, well, here's an n, buddy. There is some place after that where n is in there. There's just one place. There exists just a single place, a location past there. So it's not saying for all n past that big N. It's saying, you tell me where you want to go, and I can always find some place after this where, yep, I'm in there, right there. And you like move out here, and I go, yeah, this one falls into the set. So that's frequently. So now, this definition eventually implies frequently. So eventually would mean this. Let's see, so I've got my set A right here. Eventually means I'm going like this. Da, 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 da. And maybe 10,000 sequence points later, from there on out, I'm inside there. And that means if you tell me, hey, at some point, find me a location in the sequence past that point that falls inside A, I've got them. I've got infinitely many of them. So this is the stronger one. So eventually implies frequently, but frequently does not imply eventually, and kind of the case in point is the -1, 1 sequence. So here's one last question on that. Suppose an infinite number of the terms of a sequence x sub n are equal to 2. Is x sub n necessarily eventually in 1.9 to 2.1, or is it frequently? So I'm giving you a very specific, sorry, that's getting super shitty writing, but that interval is 1.9 to 2.1. So I've got a sequence, and all I know is an infinite number of the terms of that sequence are equal to 2. I don't know anything else. There could be an infinite number equal to any other things. Is that sequence eventually or frequently in that interval? Come up with an example sequence to support your conclusion. And maybe an example to say, it's definitely not this because this example. Anybody think they could have two different sequences? Beautiful. Got something thinking. Okay, cool. Still thinking. Okay, cool. So I'll just pop up 2 examples I've seen so far. That was Christian's. And this was Camille's. Interestingly related, not the same. Like it. Drop these out. So let's see. Yeah, these are cool. Cool little twists on each other. So in the interest of going on, maybe check out these examples. Let's go through these two. Ladies, do you have one you thinking, or still thinking? Okay. Is it okay if we go ahead? So this was Christian's example. And what set were you saying it was in that set, the one I gave down there, right? So this sequence here is frequently, that's what you were saying, right? That it is frequently in there. So this is 2, and then 2.1 is right there, and 1.9 is there. We can think of our set as that 2 right there. This sequence it will continue to visit that strip forevermore. So it's frequently there, but it's not eventually there, because there's always going to be another one that pops out of it at some point. This was Camila's, and the same thing here. It's just the popping out's a little bit further away. So her set was the sequence her sequence was the one that alternated between 2 and -2. So notice that it is frequently in this region, but it is not eventually in there, because there's always going to be another -2 coming along. Good work. Does that make sense? See, does that sound good to you? Yeah? Okay. All right, let's do a little bit of like moving in the book, talking about some things, but it's good to play like this together. I guess I have some notes or something for today. We're basically going to look at some limit theorems, and there's some really important techniques in here that I want us to see together. That may be handy for 2 of the problems that I gave you all. I'm kind of suspecting no one started on those last 2 problems on the homework. Is that true or false? That's true or false? You got something?
Yeah.
How's it feeling?
It was very tough. I have ideas for both of them.
Okay.
I'm not sure how right they are.
No, that's great, and that's the cool thing, just getting some ideas.
Took a while.
Okay, awesome. That's good. Yeah, they're not easy. They are absolutely not easy problems. And there's some techniques you're kind of going to have to figure out on your own. But some of the stuff we'll talk about today kind of might help illuminate that process, I think. So let's take a look at some limit theorems and see how to prove them. So this is theorem 9.1, I think, in our book. 9.1. Every convergent sequence is bounded. Let's just look at that statement for a minute. If I know a sequence converges, it is bounded. What is the contrapositive of that statement? So the contrapositive, just so we have it here, because it's actually kind of a useful result on its own. What is the contrapositive?
Would that be that every divergent sequence is unbounded?
That is the negation of it. That is not the contrapositive. Close. So here's, if I have an implication, P implies Q. What you were saying was this, Christian, not P implies not Q. But that's not the contrapositive, but it's close. What's the contrapositive? How do I form that?
P implies not Q?
That is, no, that's not that one.
It'd be like not P does not imply Q.
That's not it either, but we're almost exhausting the possibilities.
It has to be not P implies Q then.
That we've just exhausted another one.
Oh.
It is not Q implies not P. That's the contrapositive. That's good. We got there. Really important construction. It will be something you'll use many times in your mathematical career. So this is the contrapositive. And I like to think of it like this. If I have a light switch, and you've probably seen me do this before, and that switch represents P, and then I have a light bulb, like old school incandescent over here. And when the switch, so P true means the switch is closed, P false means the switch is open, Q true means the light is on, Q false means the light is off. So if I say P implies Q, it's kind of a situation like this, that I know that if I flip the switch P, Q turns on. The contrapositive says, if this light bulb is not on, then I know this switch can't be flipped. See how that works? Now, one of the things with these implications is, this doesn't necessarily imply Q equals P. That is the converse statement, and they are not the same. Because this light might be on, but there actually might be another switch that turns it on. So this isn't the same as this. If I did have if and only if, let's talk about this just a little bit. If I had P if and only if Q, then that means I know there's no other ways to turn on this switch. So that if the light is off, light is on, it has to be the P is on, and if P is on, then Q has to be on. But what we've got right now is just this implication, and this is the same statement. These are logically equivalent. If you made the truth tables out, they look exactly the same. So the contrapositive of this is what? Well, let's actually turn this into an implication. So what implies what here? What's P, what's Q?
P would be convergence and Q is boundedness.
There we go. Convergence implies, I like how you said that too. Convergence implies boundedness. So what's the contrapositive? Not,
Bounded implies not.
there we go, yeah. Not bounded implies not convergent. So if I've got some sequence and I know it's got pieces of it flying off and becoming infinite or minus infinite, it can't converge. Kind of makes sense, but it's a nice result to have on its own, that not boundedness means you cannot converge. So even if I have a sequence like this, x sub n equals n, just keeps on cruising, never settles down to anything. Okay, so just wanted to, not bounded implies not convergent. I wanted to practice all sorts of things today. All right, so we're gonna prove this. Let's see if it makes sense first. Let's draw our picture. And let's get the proof going. So proof, we're going to assume we have this sequence x sub n, and x sub n converges to a number L. Think of the picture. Here's L. I'm going to draw a little dotted line. Here maybe x1, x2. What's happening as I move to the right? What's the picture doing as I move to the right? Settling down, yeah, headed toward L, right? Maybe oscillating around it, maybe not even oscillating in a regular way, but they're getting closer to L in the sense that you tell me how close you want to get to L, and I'll find a place where from that point on, we're that close. So remember, this limit statement is a call and response game. You tell me how close you want to be, I'll find a place where from there on out, you are that close. Okay, so here's our picture. So let me draw it again. And remember, this is for all epsilon. Let's actually write that up. We know that for all epsilon greater than 0, we can find capital N so that, and I'm going to write it out as a double inequality. L minus epsilon is less than x sub n is less than L plus epsilon. Here's L. This is going to be my plus epsilon minus epsilon. Let's draw a sequence that doesn't fall into there for the first 4 terms, but then after that, it's inside there. So notice we have for all epsilon here. So what we're going to do is we're actually going to pick a specific epsilon. So let's let epsilon be 1. That's nice. Yeah, so now our picture looks like this. Here's L plus 1. Here's L minus 1. So looking at that picture there, how would you figure out, looking at this picture, the largest magnitude that any of the x sub n's can be? So looking at this picture, how can I figure out a bound on those things? So let's start here. From here on out, not looking at those, if it's all inside here, what are they all less than?
The one to the left of it?
When you say that, I'm sorry, what do you mean by left?
Well, I guess like above L.
Above L.
The ones that are, as you move leftward, like they keep getting greater, I guess, like as you, like, cause it's converging to L,
Mm-hmm.
like they're kind of like
Mhm.
moving downward.
Yeah. So what is this? Yes, they're close to L. What specifically is this one less than? Give me a number that one right there is less than.
I guess L plus 1.
The top. Give me a number this is less than.
L.
Give me a different one that's similar to one you mentioned already.
L plus 1.
L plus 1. Notice how, if I say this, so here's my n, here's my response. I picked epsilon as 1. I've got this tube that's 2 units wide, sits centered at L. From this point on, all the stuff inside here, its absolute value is less than L plus 1. Because it's under that number. Let me stop. Christian's smiling. I'm not sure why he's smiling, but I'm going to find out. Are you smiling because
No, there's like the last problem on that homework is similar to that.
Yeah.
I think I was on the right track.
Good. I told you this might help.
Yeah.
Do you all see what I'm saying here? Tell me. And if not, you know I'll say it again and again. So I can find this n so that this is true. And I'm only writing this L like this because it looks like it's positive here. Otherwise, I'd have to put absolute value of L there. If this was all underneath, then I'd have to take the absolute value of L. Okay, so we've got all these x sub n's bounded by L plus 1. But then these are clearly bigger than that. How can I get around this? So I want one number. I want one freaking number, m, so that x sub n is always less than n. I've got infinitely many of them bounded right now. I've got the tail end of that list of numbers completely bounded. What can I do to get a number so that they're all under that number?
say all, are you talking about like all of the X of n?
Yeah, yes, sir, yeah, so for all n. So for n equals 1. So here's n equals 1, right? Here's n equals 2, here's n equals 3, n equals 4, and it looks like we've got x sub n is less than l plus 1 for n bigger than 4. Just based on this picture here. Anything, because here's this 4, right? 4 is not in, this isn't true for 4, x4. It's not true for x1, x2, or x3. How can I get a number? Build it. Don't think crazy. Just think, I'm building something. What measurement will work?
Be able to take the supremum, or would that be too quick?
Of what?
Of X of n?
We could do that. Of all the x sub n's, is that what you're saying?
Yeah, or like assume it like the set that it creates, like if it's like.
Yeah, we could do that, and we would want to do that if we had like. So first up, check this out. We've got.
Would you be able to assume that like if at that certain point n equal, or when n is greater than 4, everything is like within that like epsilon band?
Yes.
Then you could say that like the first couple values, like up until that point, you could take the supremum of that, and then just kind of assume that like the epsilon band is just less than those. So those don't really matter when you're taking the supremum.
There you go. But we just need the maximum. So supremum's used when you've got infinitely many things you want to take an upper bound on. But here, I'm only going to have a finite number because I've got the infinite collection bounded by L plus 1, right? From this point on, I'm done. That's the troublesome spot. I've got these guys, the tail end of the sequence, bounded between here and here. Now I'm going to look for the biggest one of these guys and use that as a potential upper bound. So I'm going to write this out. I wanted to talk this through. So let's actually get this done. So we're going to pick epsilon as 1. We can find a big N so that the absolute value of x sub n minus L is less than 1, because that's my epsilon, when n is bigger, little n is bigger than that cutoff point. And let's take that inequality and break it apart a little bit and make it look a little bit easier on our brains. So I'm going to write it back up here again. This means that minus 1 is less than x sub n minus L is less than positive 1, which means that L minus 1 is less than x sub n is less than L plus 1. So that's kind of this picture right here. And here's the end where they fall inside that strip. So let's draw the picture over here just to make sure we have it again. Here's L plus 1, here's L minus 1. And what I'm saying is I found the cutoff, capital N. We're not even thinking about what's before that, but all the x sub n's live inside there then. So all x sub n past this point fall between L minus 1 and L plus 1. Now we've got to be careful because what if that L had been negative? So let me just to like, because I'm about to do something here, and this confused me when I was a younger mathematician. What if that L had been down here? And then I've got, here's L plus 1, here's L minus 1. Same situation, just shifted down. And we'll say that at this point, here's my capital N. From that point out, everything's inside there. So at this point, what can I say about the absolute value of x sub n? So the absolute value of these x sub n, up here it's easy, because I can say, oh, well, the x sub n up here, since L is positive, all have absolute value less than this positive number plus 1, looking at that picture. But down here, it's not quite the same. So down here, because now the L minus 1 is the furthest away. So what I'm going to do down here is I'm going to say, the absolute value is still just less than, so think about what happened. This is a negative number here, right? And I'm going to make this value as positive and as large as possible. And so to do that, I'm going to take the absolute value of L. Well, I'll show you with a specific example and add 1 to it. And then that's going to work up here too, where I say that it's less than the absolute value of L plus 1. So what the hell am I talking about? Let's look at a specific example so you can see this. Let's say L equals -3. So here's -3. Here's L plus 1, so this is L. Here's L, sorry, here's, yeah, L plus 1. And L plus 1 here is -2. And L minus 1 is -4. Right, equals, sorry, that's super shitty writing. So L plus 1 equals -2. L minus 1 equals -4. And I've got all my x sub n's living in here. And I want to say something about their absolute value. So notice that if I take the absolute value of L, that's 3. And if I add 1 to it, that gets me 4. So that's another way to get this outer bound in this particular case. So that was always kind of confusing to me, and it really just helps to look at this specific example. So what we're going to say then is, so x sub n is less than the absolute value of L plus 1, and that covers L is negative, L is positive. And if L is 0, it's good too. We're within 1 unit of 0. I don't think anybody ever explained that to me. And so I usually try to bring in the stuff that troubled me for long periods of time for y'all, so that at least you've heard it once. But this happens when little n is bigger than n. So now we've got all the stuff covered past big N, but there's these other elements. There's these guys that came before that. And so we're going to write their absolute value out. So, but the overall bound on absolute value of x needs to account for, and let's write them out. Magnitude of x1, magnitude of x2, magnitude of x3, blah, 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 up to magnitude of capital X sub capital N. Because we're moving past that. Like this would be capital N plus 1 is where we're starting here. So we've got to account for these. So here's what we're going to do. We're just going to set our max M, our bound M, to be the maximum. The maximum of these guys, so pick, if maybe one of those is bigger, who knows? X3 up through X sub N, and then comma absolute value of L plus 1. So remember, this bounds the tail. And if we do it this way, now we've constructed. That's why analysis always worked so good for me, unlike abstract algebra, where I didn't feel like I could build shit. And here I'm building something. It's literally like it's a construction project with infinity involved. But notice how we turned infinity into something that was finite, and we kind of were like, the infinite part, there's the bound on it. And we got that from this definition there. I want to do one more. Which kind of, so that's a very niche argument. Kind of just shows up for this. I want to show you one that's more classic, and you're going to see about a gajillion times this semester. Probably aren't going to see this one that many times, but you are going to see the next one many times, and you'll probably see it on an assignment that you might be working on or have started working on, that you definitely will be working on before Wednesday. So I don't know what theorem this is. Theorem probably 9.3, I guess. Suppose that I've got a sequence x sub n that converges to x, and a sequence y sub n that converges to y. Then the sum of those sequences, so if I add the sequence terms, that will converge to the sum of the limits. Let me write that out a slightly different way. I.e., if limit as n goes to infinity of x sub n equals x, limit as n goes to infinity of y sub n equals y, then limit as n goes to infinity of x sub n plus y sub n is x plus y. So in these kind of limit proofs, kind of want to look at the target, and we need to choose. We're going to take arbitrary epsilons, and we need to choose n's that do the thing we need. So let's look at what we need before we even start writing a proof. Do a little scratch. What do I need? So this is scratch. We need, so given some epsilon that's positive, we need some single n's so that x sub n plus y sub n minus x plus y, so this is the sequence, this is the result that I want. Here's the limit, L is less than epsilon. So to show this, I pick an arbitrary epsilon, and I show that no matter what that epsilon is, I can produce an n, so that this happens when little n is past that point. So now let's take a look at this. So again, this is scratch. I'm kind of working backwards, really, in the end. So this thing right here, I could use the triangle inequality on. So recall this, that the triangle inequality says that. So if I took this thing here, let's write it out, x sub n plus y sub n minus x plus y is less than or equal to, by the triangle inequality, absolute value of, oh wait, no, not yet. One little move. Think about what we know. We know about x sub n, we know about this, and we know about this. Right? We know stuff about those. We know how to get those less than things. How can I move this closer to something that looks like those? how do we get the x sub n with the x and the y sub n with the y before we make a move? So we're just gonna manipulate this stuff inside here. Any ideas on what might be good?
Could you just kind of group them, I guess? Like,
Yeah, what's the grouping?
well, so, if you distribute the negative through to x and y,
Yeah,
you just do x sub n minus x,
yeah,
and then y sub n minus y.
yeah, like that. Check it out, make that move. Now it's starting to look like this, and now I'm gonna triangle inequality. So here I'm gonna have x sub n minus x, here I'm gonna have y sub n minus y. And with the triangle inequality, so triangle inequality, this is less than or equal to x sub n minus x plus y sub n minus y. And now I've turned understanding this into just knowing stuff about these guys. And so I'm gonna do all the work here. I can control this. I know how to make this less than whatever you tell me. I can make this less than whatever you tell me. And by picking the right n. So we're just gonna pick an n that does something for this, a different n that picks something for this. And we're gonna take the biggest of those two n's and it'll do both those things at the same time. So here's what we're gonna do. Here's our proof. That's the heart of the proof. There's a little magic here. So let epsilon be greater than 0. You'll see I'm kind of doing this backwards. I did my scratch. I'm hiding my trick. Since x sub n converges to x, there exists a capital N sub 1. So I'm picking n1 such that x sub n minus x is less than epsilon over 2. This is the first time we've seen this trick. It will not be the last time. I'm going to split the epsilon that I want this sum to be less to in half. I'm going to make this less than half of it and this less than half of it. And then the sum will be less than the whole thing. When little n is bigger than n1, and since y sub n converges to y, there exists a different n, possibly the same, but I don't know, such that y sub n minus y is less than half of that epsilon I'm shooting for when little n is bigger than that. We're almost done. We'll be done. Just a few minutes. Hang on. Thus, we're about to take it home. Absolute value of x sub n plus y sub n in parentheses minus x plus y, like that. I'm going to show my little trick. This is equal to absolute value of x sub n minus x plus y sub n minus y. That is less than or equal to, by the triangle inequality, which I mentioned being a super important thing, the sum of these two things and this is less than epsilon over 2 plus epsilon over 2, which happens to add up to epsilon by design, when little n is bigger than capital N, where capital N is just the biggest of those two n's over there. So capital N equals max of n1 comma n2. And that's the end of my proof. That's a lot today. That's good. So one thing I'd like you to maybe try to do on your own, just before we meet, remember we're not meeting on Wednesday, but I'll probably create like a video that has some problems and you can work along with me. But what I'd like you to try to prove is this. Prove that if x sub n converges to x, and k is a constant, then kx sub n converges to kx. Very similar.
That last part of that last proof.
Oh, yes, sir.
Is that like where n is the element of? Or
No, sorry, equals. Sorry, yeah, where big N is equal to the max of those other n's that I picked. Sorry. Does that make sense?
Yep.
Awesome. Yeah, so try proving this and realize that what you're going to want to get is this less than epsilon. You have this to work with. Here's what you want. What do you have to do here to get this to happen? Similar idea, but only one sequence floating around. All right, good stuff, friends.